What if I told you that time travel does not exist only in science fiction stories? Would you believe it? Because it has solid theoretical foundations in physics as a cornerstone. And this all starts with Einstein's theory of relativity. Before Einstein, Newton's concept of absolute space and time had dominated the scientific world for centuries. At that time, people believed that time flowed like a uniformly running river. Whether you were on Earth or on the Moon, the rate at which time passed would not differ at all. This theory matched people's everyday experience and seemed perfectly reasonable in a low-speed world. However, in 1905, Einstein's special relativity was proposed, and it completely overturned this understanding. It revealed an astonishing fact to us that time and space are not independent, but are tightly connected. More importantly, time is no longer absolute, but is relative. The speed of an object's motion can affect how fast time passes. This is the time dilation effect in special relativity. The core of the time dilation effect is that time will dilate due to speed. Imagine a stationary photon that oscillates up and down once per second. Now imagine a photon moving at high speed. The path it travels is longer than the stationary one. This means that the moving photon takes more distance and more time, which means time has dilated. This rule can be precisely described by the time dilation formula. If you could travel at 0.5 times the speed of light, then according to the dilation formula, time would slow down by a factor of 1.15. This means that while you pass 52 seconds on your spaceship, an observer on Earth will pass 8 seconds more. If you travel at 0.99 times the speed of light, time will dilate by a factor of 7.1. The closer you get to light speed, the greater the factor of time dilation. Besides speed, gravity also causes time dilation, making time slow down. After special relativity, Einstein's general relativity further expanded our understanding. This theory states that gravity is essentially a geometric effect caused by spacetime curvature. The greater the mass of an object, the stronger the curvature it produces, and the slower time passes near it. Imagine this: a massive object bends spacetime. When a photon travels along this curved path, the path it takes requires more time than a straight line would. This means that near a strong gravitational field, time flows more slowly. Therefore, as long as we control speed and gravity, we can travel through time. But these two methods can take us only to the future because the flow of time is one way, as determined by the second law of thermodynamics. In an isolated system, entropy only increases and cannot spontaneously decrease, just like a shattered glass cannot reassemble itself. This direction of increasing entropy defines the arrow of time. Reversing time would require the entire universe's entropy to decrease, which clearly violates natural laws. Even if we ignore physical limitations, going back to the past would create unsolvable logical paradoxes. You may have heard of the grandfather paradox, in which you go back and kill your own grandfather, meaning you would never be born. So how could you complete the time travel? This kind of causal contradiction makes returning to the past logically impossible. Therefore, going back to the past will forever remain an illusion sealed by the laws of physics and logic.